work through this plonk tutorial that we set up a while ago, and basically it will take you. It's more technical than yesterday. So like, let me give a brief recap of what we did yesterday. So yesterday we talked about this idea of like how like abstracting away the complexity so that it allows us to like build things and figure out how things work like at a better time, that like we're able to take some of the more difficult components and we think, oh, I don't know exactly how this works, but I know what it does. And it's good that you just like black box it away. So like some of the questions that came up yesterday was like, we talked about like all of this, especially in the first session yesterday, we talked about the ways to use ZKPs. We made some private applications. We talked about private social media and private voting. And like after that, we never really talked about how ZKPs worked. So that's what we're going to explore today. And we're going to take the same kind of philosophical approach of like not learning exactly how every single component works, but learning how some of the like key components work so that we're able to build things with Plonk and we're able to understand how things can be leveraged to optimize our systems. So today's presentation is going to be, there's this tutorial that we're going to work through together. So let me set up the tutorial on the screen. I need the password. I have it here. Oh, that's all right. Oh no. Vu, could you help me set this up? Thank you. Okay, so yeah, so we're going to work through this tutorial together. It involves, so this is based upon a blog post by Vitalik about Plonk, and basically he discusses, yeah. So let's just watch Vu set this up. So it's like a notebook. Yeah, here we go. So it's a Python notebook that we can kind of work through together in the browser. Yeah, perfect. Thank you, Vu. So here's the code. Yeah, so here's the code. Here's the repo. So you can just go here. Here's the instructions to get it set up. Yeah, so you just do a git pull and then you run this command, pip install -e. Cool. Yeah, so let's give like a couple of minutes to just download the code and get it set up.
Just 1 minute to share online.
Of course. Yeah, sure. Oh, did I close the live stream?
Yes.
Oh, I'm sorry. Oh, sorry. It's okay.
Do you mind?
Yeah, it's okay. Please. Okay. So like we can work through this code together. Are we good? Yeah. Okay. So we can work through the code together. Let me see. Let me share. Bring up the notebook. Just don't. Yeah. Okay. Okay. So this is the repo that the code is based upon, or this is the blog post that the code is based upon. So like basically what we did was we read through the blog post and we converted it into like Python code. Yeah. So like what does this actually do? Well, we want to make a ZKP for a very simple circuit. We're basically, the check that we want to do is we want to prove in zero knowledge that I know a number x such that this equation is true. So the equation is basically x cubed plus x plus 5 equals 35. Right? So let's just, like, there's a whole bunch of numbers that satisfy this equation. And the first thing we're going to do is we're going to write some code that finds numbers that like satisfy this equation. And basically the way we do this is we write some code to generate our witness. So let's talk about like what's happening here. But hold on, let me pause. Have people finished the first step of like setting? Do people have this on their screens? Working on it. Okay, we can have another short time to let people sort of catch up. Also, Vu is here to as like a teaching assistant to help people with setting the code up if they need help. So if anyone needs help, please let us know and we can help. I don't know if people on the live stream are having problems. They can ask in the chat. But like basically, what you need to do is you need to go to this repository, and you just need to do git pull this repo, and then you need to do pip install -e dot, and that should install all the dependencies. But I think you also need to install Python notebook. So that will be pip3 install notebook, something like that. Yeah. So I'll write that up over here. So you do git pull, and then you do pip install -e dot. Oh, so you have to do cd plonk tutorial, and then you do pip3 install, and then you do pip3 install notebook. And then what's the final command to run? I think it's like notebook. Oh, it's what? Python 3? Notebook? Is that right, Fu? Oh. -m. -m. Okay. Okay. So that's how to get the notebook set up. And when you finish that, a link should pop up in your terminal. You click the link and you end up here on this page. And this page will basically let you just run through and execute all the code that we have. So like there's two versions of this. There's the like hard version and there's the less hard version. So the less hard version is that we have all of the solutions are in the notebook. That like as we're going through, you can see here that like this is the solution to the first part, and you can just like execute it. And the idea is that like if you're getting started or you're not so confident, you can execute the code and you can see what's happening in the code. And like the idea is that like as you read the code, you'll get better understanding of how it works. The hard version of this is to like delete the code and to sort of re-implement it. Treat this as the like solutions and like in parallel try to write it yourself and then see if it matches the actual results. So yeah, this is our plan for today. We're going to work through this tutorial. So this tutorial kind of has like 3 components. The first component, okay, so there's actually several components, but we're going to skip some of the components because they're like a little bit complicated, and like we're going to use our idea of like let's just black box the things that are hard, and we can come back to study them later, because studying the pieces that are easy is already going to help us a lot when we think about how to make things with ZKPs. So this tutorial has 3 parts. The first part of the tutorial, what's wrong? Okay, sorry. The first part of the tutorial is going to talk about how can we convert our program. This is our program here. This is a graphical representation of our program. And this is like a mathematical representation of our program. So like basically we have this input x, we multiply x by itself, we multiply by x by itself again, we multiply x squared by x, and then we add it to x. So that's x cubed plus x plus 5 has to equal 35. So the first thing that we're going to do in this tutorial is to take this like mathematical program, convert it into like sort of into like 3 columns, and then we're going to convert those 3 columns into like a polynomial. And the polynomial is going to verify, is going to be a series of checks that verifies all of these requirements. That's our first step. The second step is, okay, so the step that we're going to skip in the middle is about copy constraints. And the what a copy constraint does is it just makes sure that like this equals this, that like this wire equals this wire. Like a copy constraint means that we just take the output of this gate and put it as the input to this gate. That's a copy constraint. We're going to skip that. We're going to block box that out. We're just going to say that, okay, we know a way to do this. Let's not worry about it right now. That's so that's the first thing we're going to skip. After that, we're going to talk about FFTs, fast Fourier transforms. And fast Fourier transforms is just an efficient algorithm to divide one polynomial by another. Because it turns out that like it's going to be really important that we can divide polynomials, because that's going to be part of our prover algorithm. The third thing that we're going to talk about is polynomial commitments. We're going to have a way to represent our program as a polynomial, but like these polynomials are really, really big. So we're going to use polynomial commitments so that we can have a very small proof, right? We're going to turn these very, very big polynomials into very small polynomial commitments. And then we're going to open these polynomial commitments and verify that our proof is correct. And that's what we're going to do today. So we're going to take this like difficult problem of like how do ZKPs work, and we're going to turn it into like a simpler problem, to 3 simpler problems of how do we represent something as polynomials, how do we find ways to divide those polynomials by each other, and how do we have a very succinct way of representing those polynomials and opening them. So that's the plan for today. So how are people doing on the first step to set up the workbook? Ah, okay. Okay. Yeah, you go. We will help you.
Khi nào nói á, cầm mic của chị với. Vũ. Đưa cho bạn nếu mà cần hỏi thì nói hết mic lên.
Cái này cái lệnh của ông ấy, lệnh của nãy nó bị sai.
So we are missing the third command with the dot.
Oh, right. Okay. This one. This is a dot.
At the below,
Sorry?
the below command is missing the dot too.
This one.
Yes. Yes. I think.
Oh. Okay. Boo was gonna fix it. Can you use this one? Thank you, Boo. Okay, so let's start to talk about our code here. So like the way that a Python notebook works is that it has text, but it also has code. So if you want to run a box, you just click the run. And basically what that will do is it'll execute all the code inside the box, and it'll skip everything else. Thank you. And it'll skip everything else. So we've just run the first one, run the second one. There's no code here, so we're just kind of skipping them. So this is our first actual code. So this is generate witness. So like you can see here that we have our program that we want to check. We want to check that x cubed plus x plus 5 equals 35. And like the way that we do this is that we convert it into like 3 different columns, A, B, and C. So let me draw on the board what A, B, and C look like. A, B, C. So I think that like the way that A, B, and C works is that like basically what we do is we do A plus B equals C, or it's A plus or multiply by, plus slash multiply by. Yeah. So this is our constraint, right? So if we let's make a simple program, a simple constraint. So our first simple constraint can be like 1 plus 1 equals 2, right? So how does this look like in our Python notebook? It'll just be 3 lists. A, B, and C are lists. So if A equals 1, B equals 1, and C equals 2, this is our first kind of constraint. Oh, we also have to have some way of representing the plus and the multiply. Well, let's just simplify it as just being a multiply for now. And like later we can figure out exactly how to. Yeah. Let's just do a plus all the time here. Yeah. And later it's going to be a plus or a multiply. And we'll probably have a way of representing that soon. Okay? Yeah. Make it bigger, yes. Yes. Okay. So it's A plus B equals C. So if A is 1 plus B is 1 and C is 2, then that's an example of our first constraint. So this is how we're going to represent our constraints in our system. We're going to represent them as lists, okay? And that's what we're doing here. We're basically making this list of 3 different things. So like this constraint is very simple, right? Because this constraint is basically just saying that 1 plus 1 equals 2. But like another thing that we can do is instead of doing like 1 plus 1 equals 2, we can do like variables inside here. We can say x plus 1 equals 3. Okay? And that's another thing that we can do to represent our circuit, because instead of having just all constants, we can have variables. So, for example, in the program that we're trying to write, this one, we have a variable x. So we're able to also include variables in the description of our program. And this is how we describe our program. So like it's important right now to take a moment and think about the parallel between this and when you write some ZKP circuit. Maybe you all have experience making circuits with Circom. maybe you made some circuits with Zocrates or Bellman or Halo 2 or like some of the other ZKP tooling languages. And like if you did, you often have this time where all that you do is you make constraints. And like this is what we're doing here. It's a similar kind of like pattern. We have our new language, but our new language is very, very basic. It's basically a list of checks that we're applying. So now let's think about the list of checks that we need to apply in order to achieve this. Okay? So what do we need to do? The first thing that we need to do is we need to realize what are we able to do inside our system. Well, we're able to do a multiplication and we're able to do an addition. So, yeah, we're able to do a multiplication and we're able to do an addition. So because we can only do one multiplication, and because we need to multiply x cubed, we can't do that in a single constraint. So what we do is we do that in two constraints. So the first thing that we do is we say, so A equals, is this big enough? Too small? A little bit bigger, okay. So the first thing that we do is we say A equals x, B equals x, C equals x squared. Right? So this is the first step in making our program. And what do we actually, this is the first step in generating like the solution to our program. So we're starting here generating our solution, and later we're going to generate our constraints, the things that make sure our solution is correct. But the first thing we're doing is we're just generating the solution. We're writing some code that will generate, given a certain x, it will calculate, yes, given a certain value, it will calculate the correct result if a correct result exists. Yeah, given an x, it will calculate the reason why this is true. Oh, sorry, that's confusing. So, okay, let me slow down. So we're generating our witness, and our witness is basically what we give to our proof to explain to our proof why this is true. This is like the evidence that you have when you go to like try to convince somebody. So our first piece of evidence is that like x multiplied by x is x, right? And that's basically this check. X multiplied by x equals x squared. And then we say we need to do another check. Okay, so let's add our next check. Our next check, so we add another check by just making our list longer. We just put in
A plus xb.
This one is plus or multiply. Yeah, this is plus or multiply. So this can be an addition or a multiplication. The way you see whether it's an addition or a multiplication is what's happening here. Because it's x squared, this is a multiplication. So like I can just do multiply x multiply x. And that's a multiplication. Okay, so that's our first constraint. So let's take our second constraint. So what's the next thing that we need to do? Does anyone have an idea of the next thing that we need to do?
We multiply the C, the result C with x again.
Yes, exactly. So we take x squared, we multiply it by x, and we get x times x times x. We get x cubed, right? So that's the second piece of what we're doing here. Taking this constraint to here. We calculate x squared in the first step. In the second step, we calculate x cubed. Okay, so what's the next thing that we should do? What's the next part of verifying our program? So look here. We've already calculated x cubed. What's the next thing that we have to do? Plus x. Yes. So the next thing we have to do is we have to take x cubed, and we take x, and we add them together. We say x cubed plus x. Right? We add them together. My handwriting always gets smaller as I go further. I have to try and make it big. Okay, so what's the next thing that we need to do? Yes, add 5. So we take this, x cubed plus x plus 5. Oh, no. That's not how it works. So we take x cubed, and we take x cubed plus x, and we take 5, and we add them together. Plus 5. Add them together. And what's the next thing that we need? Sorry, Boop? And it makes x. Oh! Good catch. Plus x plus 5. Right. And what's the next thing that we need to do? Exactly. So far we've calculated all of this, x cubed plus x plus 5. And the final thing we need to do is make sure that it equals to 35. So let's have a look at the code here. Okay, so like here's your chance to be like do the easy version or do the hard version. So if you want to just not look at the code, you can delete it and you can do the hard version and just re-implement that code. If you want to do the easy version, you can just leave the code there and we can just look and notice the similarities between what we have on the board and what we have here. Okay, so let's take a minute and notice the similarities or implement that step. Does anyone need more help to get the workbook set up? Okay, that's great. Does anyone have any questions so far?
How can we distinguish between multiplication and addition?
So the question is, how do we distinguish between multiplication and addition? So the answer to that question is that like right now, we're not applying any constraints. Right now what we're doing is we're generating our witness. We're generating our evidence. We're preparing to go to court and to prove that like x cubed plus x plus 5 equals 35 for some x that we don't want to share. And like the first thing we need to do is we need to calculate our evidence. So if you see here, this is code that like you give it an x and it will calculate all the evidence that you need to prove that that's correct. It will calculate x times x equals x squared. It will calculate x squared times x equals x cubed. It will calculate x cubed plus x equals x plus x cubed. And then it'll calculate, oh, what it's doing here is it's saying that like it has some constants. Because like it's not, yeah, so like, okay, does anyone understand what's happening here when it's 1 multiplied by 5 equals 5? No, okay, so like what's happening here is, yeah, sorry. What's happening here is that we're having a step where we're generating a constant number. That like a constant number needs to be created in the previous step so it can be copied to the current step. So what we're doing is we make two constants here. The two constants that are important. Let's look at our equation here. Like what? So we have one variable and we have two constants. So our variable is x cubed plus x. What are our constants? Our first constant is 5, and our second constant is 35. So these are constants inside of our circuit. So that's what we're doing here. We're just checking that the constant is correct. Because like what we're worried about is that someone can make some fake evidence. And they make fake evidence that like instead of putting 5 here, they put 6. And they put 6 here. Like if they put 6 instead of 5, we don't have a check that checks that 5 equals 5. And that's how basic we need to go. That's what we're doing here. We're saying 5 equals 5. We're saying check 5 is 5. Like that's like it's hard to grasp conceptually like why we need to do that. But the reason we need to do that is that we just need to be very careful because we don't know anything in our evidence. In our evidence, we're just starting from the very basic. We're saying 5 is 5, 35 is 35, x is x times x is x squared times x is x cubed. We're just listing every single thing from the most basic thing. And that includes doing like things that like you imagine you don't need to do, like 5 equals 5. So that's what we're doing here. We're doing 5 equals 5. We're doing 35 equals 35. And then we're doing x cubed plus x plus 5 is 35. Yeah, plus 5 is 35. What's up?
What if you don't? How do you know that you've covered all the, like, if you miss the 1 times 1 5 thing, how do you know that how do you know that your witness is sufficient to prove it?
So if we're missing this 1 times 5, okay, so let's set that as one of the like experiments that we should do, right? Because right now we're generating our witness, and the next step is we're making sure that our witness is correct. And like so like what you're saying is that like what would happen if we give an invalid value?
I mean, like if I think I create this witness and I like I'm doing it for the first time, I don't know that I'm supposed to check 1 times 5 is 5.
Yeah.
And it could maybe, as we're saying, someone could, my witness is not like sufficient to prove. Someone could throw a 6 or something in there.
Yeah.
And everything's invalid, but I don't realize it. I don't actually move to the next. So I have like a satisfied witness that's not sufficient.
Right.
So how do I know my witness is like covers all the?
Is sufficient?
Yeah, it's sufficient.
Yeah. Okay. So that's what we're going to do here.
But that's like if I don't put the 1 to 5 assertion.
Oh, it's not going to be there. Oh, yeah. Okay. So like we're generating our evidence, and we're going to check our evidence is correct, and then we're going to make the actual ZKP that proves our evidence is correct. So the first step is we make the evidence. The second step is that we check it's correct. And the third step is we prove it's correct. And like what you're describing here is a soundness bug. Yeah. So there's like if we don't have this check here, it will introduce a soundness bug into our proof. A soundness bug means that like we're checking our evidence, but it's possible for someone to give us some incorrect evidence that we'll still accept as being true. So that's a soundness bug. Yeah.
How do I know that I don't have one of those?
So this is like making a smart contract. Like how do I know my smart contract is secure? Like this is exactly the problem you're talking about here. It's about like a implementation problem. It's about like being confident that your contract is correct. Is that
But I guess like
how do you know that?
if you're not here and I make this like and I forget to this 1 5 thing, is there a way to prove that my contract is, or I guess there's no way to prove that it's sound or?
Yeah, it's very, so you can do things like formal verification, but that's very hard to do. The other thing you can do is you can do audit. You can ask someone to check, is this correct? Do I have any soundness bugs in my proof? But like, okay, so let's go through the whole process. Let's say that we're making into production, and there's a lot of money at stake for people who can prove that x plus 5 x cubed plus x plus 5 equals 35. We put that into production, but we forget one of our constraints, and that leads to a soundness bug in our proof. We'll get hacked. Someone will find that this soundness bug is not there, and they will be able to make a proof for satisfy. They'll be able to find an x, and they'll be able to make a proof that it equals 35, but when it doesn't. So that's the issue. That's what will happen here. So this is like a secure implementation question.
For this one, if I didn't put that 1.5 and what the constants, like what, I also have a hard time seeing how you would still come up with something that.
Sure. So let's investigate that in a second.
Okay.
Right? So like the plan for the first part of the session is to get to that point. Let's talk about like we generate our witness, we're checking our witness is correct. Let's then create our constraints. And then let's talk about an attack where we miss out one of those constraints. That will be the first half of the day. Then we'll have a tea break. And after that, we'll do like FFT and /or polynomial commitments, depending on how much time we have. Cool. Okay. So we've generated our evidence. Let's first of all, okay, so we generate our evidence. Let's see. Let's do some experiments here and see what it looks like. So let's do gen witness of 1. And let's execute this. I wonder will that print? Yeah, so that prints, right? So if we have 1, this generates our witness of 1. So this is basically saying x equals 1. And calculate all the values based on x equals 1. So the first thing that it does is it says that like 1 multiplied by 1 equals 1. 1 squared is 1. 1 multiplied by 1 squared equals 1. And that's basically saying that like 1 cubed is 1. And we do it for the rest of the stuff. It just ends up being 1 everywhere. So let's do another example. This is just generating our evidence. Let's do 0. Okay, so we do 0. We have a different output. Yeah, x is 0, so all of these turn into 0. We just end up with 1, 1, 5, and 35. So these are the values for, this is the solution when x equals 0. And then we can just put whatever we want to, 42. And this gives us another number, right? So this is our evidence. Given us our x, this is the evidence we need to provide in order to our proof, in order for our proof to be created. Because like, sorry.
Why can't we just have the last one? Why do we have to do this XX? Why can't we just have one constraint like x is plus x?
So
35?
We need to think about the limitations of our ZKP. Our ZKP can only check one thing at a time, right? It can check one multiplication or it can check one addition. That's why each of these columns is a multiplication or an addition. Yeah, so we just have like this multiplied by this equals this. So like what we're doing is we're thinking about like inside our proof we're able to do just one thing at a time. So we're describing our evidence in a way that's like one check at a time. It's kind of like another way to think about this is like you go to court and you're talking to the judge, and the judge has a very short attention span. The judge is only able to deal with like one thing at a time. So you have to present your argument in a way that they only have one thing at a time to think about. So like there is some kind of fun stuff that we can do with like more advanced CKPs where they are able to do like more than one thing at a time. You're able to make like bigger stuff happen at each step. But like that's a little bit out of scope for today. Okay, so yeah, any question?
Oh, so this is just a proof that you are giving other people.
This is the evidence for a proof.
Right. So it's not necessarily true for other people. Later, they have to verify it.
Yeah, exactly. So we could give malicious evidence here. And if we do give them malicious evidence, we could trick them. Like the conversation a moment ago was about what if we mess up and we don't give like all of the details in our proof? Could someone kind of hack us? And the answer is yes. That if our proof is not sound, then it's possible for people to like make fake proofs. Yeah. Okay. Any other questions?
On the whiteboard, the first one you use the minus, but the last one you use the plus. So it's okay.
Sorry?
The first one you use the minus is it time is, but the last one you use the plus. It's okay.
Yeah, I didn't put the 35 here just because I kind of ran out of space. Is that what you're asking?
No. I mean for the first content, first element you is s plus is time is, but the last one you use the constant the operation is plus. The computer the
Oh,
seed.
this one.
Yeah.
Yeah. Okay.
And-
So yeah, that's right. This should be 1 plus 1.
No. I mean, for the IB, you see the first element, you have the is.
This element?
Time it. Yeah. But for the last one, you use the less. It's okay.
6?
You less 5 for it. The way you compute, the way you
Oh.
generate the seed, it's at minus. It's not.
Should be 5? Oh, it's minus?
Yeah. You
Oh.
can use minus. Yeah.
5. Where's the minus? I don't see. Do you want to come and point out?
Yeah. Okay.
Here, just come.
You use the minus, right?
No, that's just multiply.
It's light, and it's here. You use the plus here.
Oh, wait. Where's the minus though? No, that's multiply.
It's light.
Oh yeah.
Minus. Oh,
Yeah.
sorry. I'm confused about.
All right. Okay.
It's
Yeah.
light and it's blood and it's blood. It's not,
Yeah. So this is multiply.
I think it's just light too.
This is.
'Cause you use
Oh.
plus here.
No, well, I'm still confused. Only use plus. Oh, right. Okay, I see what you're saying. Right. So Vu is saying that, like, yeah, well, Barry, like a minute ago you said the judge has really short attention span. He can only do one thing at a time. But like here, you're telling her to do like a whole bunch of things at a time. You're telling her, oh, x times x times x plus 5 is too many things. The judge can't handle that. And Vu is, yeah, you're dead right, Vu. But like, what I'm trying to capture here is that, like, oh, let me get my blue marker. Is that, like, this is our evidence, and like in our actual proof, what we'll do is we'll copy things. We'll say that, oh, copy this to here. And then we'll say, oh, copy this one to here. And copy it to here. Right? And then we'll say, copy this one to here. And copy it to here. Right? And this is the other tool in our proof system called copy constraints. So we are able to do additions, we're able to do multiplications, we're also able to do copies. And that's it. That's an important thing to remember. Our judge has really short attention span, but we are able to tell the judge, hey, but because this is true, this is true. And this is copy constraints. And that's an important thing to remember. And yeah.
So what we are doing is
Up the program.
Right? Yes. So like what we're doing right now is we're describing the program in a way that lets us generate our evidence. In a second, we're going to check our evidence is correct. Finally, we're going to describe our program in a way that like our evidence can be verified inside a proof. Hopefully. Okay. So any more questions? Yes.
what happens if
we have infinite evidence?
Infinite evidence.
Yes.
So we have an upper bound on the amount of evidence that we have.
Cool.
That like We can only make proofs about things that, okay, so let me talk about the trade-off here. The more evidence we have, the longer, the more checks that we have to make. The more checks that we have to make in our proof, the longer it takes for us to make our proof. The key thing and the super cool thing is, like, no matter how much evidence you have, the verification time is the same. Yeah, so even if you have like gigabytes and gigabytes and gigabytes of evidence, and the proving time takes days and days and days with like a supercomputer, the verification time is still exactly the same. So like that's one of the superpowers of ZKPs, that like the verification time is constant. But like when you have more evidence, it's more work to make the proof.
I got it.
Okay.
Okay, one more question. So why is it very fast to verify?
Why is it very fast to verify? So we'll get to that later. So like it's to do with, like, okay, let me give you an intuition that like when things are really big, it takes a long time to check them. But when you're able to compress them, make them smaller, it takes less time to verify them.
Oh.
Because it's smaller, it's less things to check. Like another intuition for this is that like when you want to check something and be like 100% sure that something is correct, you have to be very careful and very diligent. But when you want to check something and you're okay to be like 99.99999, like very, 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 very sure, you have to do a lot less work. Because that last tiny percent of certainty is like takes a huge amount of work. It basically means you have to check everything. So like those are two intuitions. Let's revisit this conversation later when we get to that part about polynomial commitments, because I think that will also help to kind of give a kind of indication to this. Okay.
Okay.
Cool. Thank you. Oh.
So
What happens if it's not any non-integer number?
What if it's not an integer?
Yeah. What happens if program is is non-integer?
So what if it's like 0.01?
Something like it.
So if it's a floating point number, this is broken. If it's a negative number, this still works. We were able to represent negative numbers inside of our ZKP, but it's like that's conceptually difficult to understand. If we wanted to make a solution, if we wanted to make something that worked for floating point numbers, we would have to come up with a way to represent floating point numbers inside of our ZKP, which is like, it's possible. Let me give like a brief intuition about how we would do that. So right now, inside our ZKP, our numbers are 254 bits. If we wanted to have a floating point number, what we could do is we could say, okay, our numbers are 32 bits before the decimal and then 32 after. And like we would be able to represent floating point numbers like that, but it's tricky to figure out. But it's possible. Gotta do the password. Okay, so let's move to the next part. Let's verify our evidence is correct. So you can see in the workbook that there's a section about evidence being correct. So yeah, you can see it here. This is basically just checking our evidence is correct. It just varies pluses and multiplications. So we just run this. So let's move forward a little bit through these steps. So we executed all of those steps. So let me just briefly explain what's happening. Okay, so this is just checking our evidence is correct, but it's not checking inside a proof. This is just checking. This is just us checking it by hand, just to make sure that, just to do some testing, just to make sure what we've said is right. And then what we're doing here is we're doing what we did above. We're just generating a witness where x equals 1, and then we're checking that that evidence is correct. This should pass. So there's an assertion error here. Oh, interesting. So, okay. So the workbook says that you should figure out why this happens by yourself, why this failure is happening. So let's leave that as like a exercise for at home, because I want to try and get to the end of the plonk everything is a polynomial section. For some reason, when we're generating one x equals 1, it fails. I don't know exactly why, but like why don't you all have some time and think about that and see why when x equals 1 the witness is incorrect. Does anyone have an idea for that? One plus 1 plus 5. Oh, yeah, I think I know why. Okay, so like, how about this? Why don't you all think about that? And after the coffee break, we'll revisit why when we try and generate a witness when x equals 1, it fails. It always fails. Let's think about that, and we'll talk about that after the coffee break. But we're not going to do a coffee break right now, although we're close to the time when we need to. We're going to talk about like the next step about we have our evidence. Now we want to start thinking about how can we use that evidence to convince the judge. But we're going to make our judge. And like the way we're going to make this judge is using polynomials. That polynomials turns out have this like superpower where if we're able to convert our witness checks to polynomial checks, then we're able to use polynomial commitments to make our proofs very efficient to verify. So that's our next step. We're going to take our evidence and we're going to convert it to polynomial form. Because when we convert it to polynomial form, it will make it easier for us to enforce our constraints. Okay, so run this. Okay. So in plonk, everything is a polynomial. Like we have our witness that we're generating as lists, but we want to convert those lists into polynomials. So the first thing that we're going to do is we're just going to make some tooling about polynomials, right? We're going to make just this function that, like, given a set of coefficients, we evaluate that polynomial at a certain x, right? So that's what we do here. And I'm going to go through it quickly just because we don't have a lot of time. This is just like, let me just do that. Let me just do an example here because examples are always easy to help us understand. So like the code here basically gives us like, let's say it's like x plus 1. Let's evaluate x plus 1 when x equals 0. So the inputs to this eval polynomial is the coefficients, which in this case is 1 and 1, and the value of x, which is 0. And when we run this code, it basically just says that it's 0 plus 1 equals 1. It just calculates 1. So if we run this eval polynomial for those inputs, we should get 1. Let me just double check, just to make sure. Eval poly. Okay. Yeah, okay, that worked. Yeah, so that's what this does. It's just code that takes like a polynomial with defined like this in coefficient form. Coefficient form is like this is 1 multiplied by x. The coefficients here are 1 and 1. They're just the powers of the terms, or it's just the value each term is multiplied by. Like we could change it like if this was 2x plus 1, 2 would be the coefficient and 2 would go here. I'm pretty sure it goes like that. Yeah, it goes like from the highest power of x to the lowest. That's what this code does. It's just a helper function. We're just going to need that later to test that our things are working well. So we just implemented it here. And then we have a whole bunch of tests here, testing that it's all correct. So that's just a little bit of setup work. We're just going to be working a lot with polynomials in coefficient form. So let's make some tooling to evaluate those polynomials in coefficient form. Okay, so it's working. So let's talk about how can we define our argument? How can we define our judge? So this is how we're going to define our judge. Right? So our witness here so these are our constant terms. So this is like how to describe this. So this is like okay, let's look at our evidence. So our evidence here is doing like different things. It's doing additions and it's doing multiplications. And it's dealing with constants and it's dealing with copy constraints. So when we define this is basically a polynomial that does like additions, multiplications, and constants, right? And basically the way that we encode a constant. Okay, so maybe we should go through this. Yeah, okay, so let's look at this. Let's look at this equation a little bit more. So QL, QR, QO, what are those? Let me bring up our picture. QL, this is QL, this is QR, this is QO. So that each time we have a gate, we have the left-hand side, QL, QR, the right-hand side, QO, the output, right? So let's have a look at our equation again. Here's our equation. QL, QR, QO. QM and QC. What's QC? QC is our constant. Sometimes we have to be able, like we're doing, like inside here we're doing plus, we're doing multiply, we're doing constant. So sometimes we want to do a plus, sometimes we want to do a multiply, and sometimes we want to do a constant. So how can we define? If we want to do a multiply, we set QM to 1. If we want to do a constant, we set QC to 1. If we want to do an addition, we set QM and QC to 0. So let's take one more second to investigate this. So let's set QM to 0 and see what our equation will look like. If QM is 0, we end up having, is it okay to clear this one? Yeah. Okay, so let's say QM is 0. So we end up having QL times AI plus QR times bi plus qc, qo times c I. Then this one goes away, and we end up with qc here too, plus qc. Okay? So that's what happens when qm equals 0. So qm is what we call a selector, and qm looks like this. QM is just a list of 0, 0, 0, 1. So when QM is 0, we're not doing multiplication. When QM is 1, we are doing a multiplication. And that's basically the rules of our that's how we turn on a multiplication. That's how we decide if we're doing a multiplication or if we're doing an addition. Okay. Similarly, we can do same thing with QC, where we can have like constants here where QC will be the constant. And if we want to do an addition, we just set QM to 0. So we have a single selector that turns on and off. Yeah. We have a single selector that turns on and off the multiplication or addition. The constant selector is defined by QC. So we have these two flags that say if it's a multiplication, an addition, or a constant. The other thing that's happening here is AI, BI, and CI. AI, BI, and CI are our evidence. That's what we're passing in as our witness. This is provided by the user. And QL, QOR, QO, QM, and QC are provided by like the setup. When we're setting up our circuit, we define QL, QOR, QO, QM, and QC. And that's how we describe our circuit. QL is like, do we take the input from the left-hand side? QOR is, do we take the input from the right-hand side? QO is like, do we have an output? Like these will almost always be 1. Because like sometimes you want to turn off the input on one side of the gate. Like for example, yeah, sometimes you want to turn off the input on one side of the gate. So like these are all the Qs are provided by when we create our circuit. And the Qs define like how our circuit kind of like is connected together. Questions?
So it is rank 1 conference.
Yes. Yeah. So this is a rank 1 constraint system where like each row we have like a single multiplication or a single addition check. And like when I say row, it's like this is a polynomial that has like many terms inside, and it's built up of like many different polynomials. And each evaluation of that polynomial is a single check. Okay, cool. So, sorry, I'm supposed to warn you when we get to the hardest parts. Like when we're coming to the hardest parts, I have to tell you, prepare, we're getting to the hardest part. So that was the hardest part. I should have told you to pay particular attention. But like, that was the hardest part, but let's just keep going. We're almost done. I think that's like one of the hardest parts of the whole thing. Like each section will have a hard part, but that was one of the hardest parts of the whole thing. So that's good. Let's just like execute the code that we have here. Just run. Yeah, so like what we're doing here is this is just adding our constraints. So we're making very simple programming language. Every time we want to do an addition, we do this. So this is a test for an addition. An addition is where QO equals -1. So let's have a look at that. So QL, QOR is 1, and QO is -1. So let's have a look at what our equation looks like when that's true. So we have this equation, and let's substitute in. Oops. QL. So QL is 1, QOR is 1. So QL is 1, it's AI. QL equals 1, it's AI. QOR is 1, it's BI, plus BI. QM is 0, QO is -1 minus CI, and QC is 0 equals 1. And that's basically the same as saying AI plus BI equals CI. That's an addition check. That's an addition constraint. So when we want to do an addition, we need to set QL and QR to 1. We need to set QO to -1. QM and QC go to 0. That's how we do an addition check. That's how we we define our polynomial. Yeah, that's how we do an addition check. And like similarly, we can do a multiplication check, and we can do a constant check. Okay, so we're almost at the end of the first half. Almost there. So this is just generating the constraints for our program. This is the last part. So like basically what we're saying is that like yeah. So basically what we're doing is we're calculating the QL, QR, QM, QO, and QC that satisfies our original problem. That satisfies this. So we've already defined the AI, BI, and CI. That's here. A, B, and C. And now we're just converting the checks into a polynomial. Instead of checking it here, we're putting the checks inside our polynomial. Yeah, so we put our checks inside our polynomial, and it's relatively easy to do. So we say that like we're basically taking A0, B0, C0, and we're saying, okay, that has to be a multiplication, because that's what we're doing here. Do multiplication. And we're taking the second set. That has to be a multiplication too. That's x squared plus x equals x cubed. Then we're saying, okay, we need to add a constant, right? We have to say that 5 equals 5. Then we're saying then we do an addition, then we do another constant where 35 equals 35, and then we do the final one where 35 equals x cubed plus x plus 5. Okay. This is how we define our proof. Okay, so do people have questions? Okay, I understand that we went very quickly through the last part. So if people don't understand exactly what's happening, let's black box it out so that we can like continue with the tutorial, and later we can dig in more into those specific questions. So basically what we did in the first part, we spent a lot of our time today just defining our evidence, building our evidence to convince our prover. And because of that, we sort of didn't have a lot of time to define how our prover works. And like we sort of rushed through that. But basically what we did was we changed our checks into being polynomials. So now we have a polynomial that checks all of these checks that we described earlier. It applies each check, and then that's it. We don't know about how to verify our polynomial. We're going to talk about that later. We're also I think we're either going to do about FFT or verifying the polynomial. I think we should probably do verify the polynomial because it just seems like we'll have more time. It just seems like it's worth the time to dig in deeper there. So let's do that after the break. Let's have a break now. And the one problem for the break to think about, or if people want to discuss, is this question here. Why does this fail when x equals 1? It fails because the assert 19 fails. Why does that fail? So we're basically generating our evidence when x equals 1, but it fails. So that's a good thing to check or to think about. If people figure it out, let me know, and we'll discuss it at the end of the break. Good job, everybody. That was a lot. Let's have a break now, and after that, we'll explore other things that you don't have to understand exactly all of the things that happened so far in order to still get benefit from the last part. So okay, thanks, folks. Let's have a break. Good job.
Can you share again on your screen?
Yeah, sure.
Just
Yeah.